Welcome to EDU World Space.
The first thing we will do for this problem is write down the position vectors for the three parts of the space vehicle after they separate. So the position vector for A, we'll call it RA, is given as 250I plus 250J. So we'll write it in its basis vector notation for I, J, and K, plus 2250K. For B, the position vector is 600I plus 1300J plus 3200K. And finally, for part C, the position vector is minus 475I minus 950J plus 1900K. Since there are no external forces, linear momentum is conserved. And from the conservation of momentum, we can get the following equation. So the conservation of momentum tells us that initially the spacecraft is together, and the spacecraft has mass, which is the sum of the masses of each of the fragments, ma plus mb plus mc, and has velocity v0. After the explosion, the momentum of the system is the momentum of each fragment, mava plus mb vb plus mc vc. So if we rearrange this equation, we can solve for vector VA. VA, if we rearrange, is MA plus MB plus MC all over MA multiplied by vector V0 minus MB over MA times VB minus MC over MA times VC. And simplifying this, we get this to be 6 V0 minus 2 VB minus 3 VC, since we know the masses of these three fragments. So now that we have an expression from the conservation of momentum, we can write this as follows. Since essentially we have V0 and we have VB, we can write this as 6 times V0, which is 1500 in the K direction, minus 2 into VB, which we are given again to be 500I plus 1100 J plus 2100 K, minus 3 times VC, and VC is the only vector that's not really known here, so that's 3 times minus 400I plus the Y component of VC in the J direction plus the Z component of VC in the K direction. So the Y and Z components of VC are unknown. And so this simplifies into minus 3 VC y in the j direction minus 3 vc x or vc z, the z component multiplied by basis vector k plus 200 I minus 2200 j plus 4800 k. So we can see from here that we can find the x, y, and z components of VA. So VA x is equal to 200. Looking at the I components, from the j components we get that VA y is equal to minus 3 times the y component of VC minus 2200. And finally, the z component of VA is equal to minus 3 times the z component of VC plus 4800. So now we will use, so we've used the conservation of momentum, we'll now use the conservation of angular momentum about the origin. So the conservation of angular momentum about O. And from here, we can see that the angular momentum after the space vehicle breaks apart, we'll call it HO2, is equal to the angular momentum about the origin, initially HO1. But since the vehicle passes through the origin, HO1 is 0. And hence we get that HO2 is equal to RA cross with the linear momentum of A, MA, VA. So this is the definition of angular momentum, R cross P, plus the position of BRB cross with MB, VB, plus the same for particle C, RC cross MC, RC. And this is equal to 0. So it's HO1, the initial angular momentum, is 0 when the spacecraft is at the origin. So if we divide this equation by MA, we get that this is equal to RA cross VA plus MB over MA times RB cross with VB plus MC over MA into RC crossed with VC. So all we've done is just divided both sides by MA. And this, if we simplify it even further, becomes 3. So we do some mathematics, we get 3 into RC minus RA. Remember, the R's are the position vectors, cross with VC plus 6 RA cross with vector V0 initial velocity plus 2 into RB minus RA cross with VB. So the conservation of angular momentum gives us this. But since we have expressions for our position vectors R and our velocity vectors VA and VB, we can calculate this by substituting those values in for each of those position vectors. So this, in essence, becomes minus 2175 times vector I minus 3600 J minus 1050 K cross with VC plus 1500 I plus 1500 J plus 13,500 K, and that's crossed with initial velocity V0 plus 700 I plus 2100 J plus 1900 K cross with VB, and this is equal to 0. So if we use the cofactor method as an example and we calculate VCX, VCY, and VCZ using this cross product, or the sum of the cross products, we can then get a vector which we will resolve into components I, J, and K. So the I component of this vector is 1050 VC in the Y direction minus 3600 VC Z, so the Z component of VC plus 2,250,000 plus 2,320,000, and that's equal to 0. So taking the J component of this vector, we get 2175 multiplied by the Z component of VC minus 1050 times the X component of VC minus 2,250,000 minus 520,000 is equal to 0. And finally, the K component is 3,600 times the X component of VC minus 2175 times the Y component of VC plus 0 minus 280,000 is equal to 0. So we know that VCX is equal to minus 400 feet per second. So if we go back to the initial equation for VA, and we'll call this equation 1, and we'll call these three equations equation 2, equation 3, and equation 4. We can find from equation 4 VC of y, since we know VC of x to be minus 400 feet per second, and hence VC of y is equal to minus 790.8 feet per second. So the y component of the speed of v is minus 790.8 feet per second. And then from equation 3, we get that the z component of vc is equal to 1080.5 feet per second. And then since we have the speed of c, we can get VA. And VA is equal to, from equation 1, 6 times 1,500 K minus 2 into 500 I plus 1,100 J plus 2,100 K minus 3 into minus 400 I plus 700 and 90.8 J plus 1,080.5 K. And that gives us VA to be, so this is the speed which we required to calculate the speed of A after the explosion, which is 200 feet per second, I plus 172 feet per second, J plus 1,560 feet per second, K.